Good morning, good afternoon, good evening, whatever time you're watching this. Another video, we will be discussing about the derivation of the acceleration due to Earth's gravity in this very short video. As we all know, that the gravitational acceleration due to gravity is definitely 9.8 meter per second squared, and this particular value is very familiar to us. In some other books, they will just have to say 10 meter per second squared. And since it has direction, so depending on the problem, since 9.8 is our acceleration due to gravity, so acceleration is a vector, so we can definitely assign some sign convention to it. It is always downward, so we sometimes put negative in our value here. It depends upon how we use it in each problem or the type of problem. Okay, before anything else, don't forget to, of course, subscribe to this channel for more content like this. Thank you. All right, so the first thing we will do is to set the gravitational force equal to weight. And the weight force, if you could still recall, and of course, don't forget it's mg. So we will try to equate Fg, which is the gravitational force between two objects between with respect to their radius from their centers. So we will equate it to weight force. Again, weight is mg, so we will put mg here. In this case, instead of writing Fg in our formula to get the gravitational force, we will use mg here. Hold on. Fg is equal to the gravitational constant mass of Earth and mass of the object. I will just put this kind of symbols or representations here. Let me be the Earth's mass, and let mo be the object's mass. And of course, we have to divide it with the radius r. But we will have to equate Fg into the weight force. So instead of writing Fg, we have to put m, but this time the mass is, let's say, the mass on Earth. So we can say that there is an object with a mass, and let's try to find out what will be its acceleration due to gravity if it is being interacted to the Earth itself. So we have G M E M O R squared. Remember, ME is the mass of Earth, and then MO is the mass of the object interacting with the Earth. All right, so we have to really remember the constants of our calculation just to get the target. We need to have a value of negative, yeah, because it pertains to direction, negative 9.8 meter per second squared, or simply the absolute value of it. So again, we equated Fg equal to the weight force. So instead of writing Fg is equal to gravitational constant times the mass of Earth, mass of object, radius squared. Instead of writing Fg, we have to change it to mg. There you go. Let's plug in the values, but before that, we have to know that the goal for this video is to know the gravitational value, 9.8 meter per second squared. So we have to isolate g in this side of the equation. So in order to do so, we have to divide both equation by the mass in order to isolate the g, or the gravity. In this case, we need to clean it up first. Mg is equal to, remember, this will be mass of the object, mass of the object. the mass interacting to the earth. So we have to know the acceleration due to gravity, okay, to the earth's gravity. In this case, we will just clean it up here. We can factor it out. Say, for example, this will be gravitational constant times the ME over R squared, and we will pull out MO, or the mass of the object. So that when we will divide both equation by mass of the object, cancel, cancel, and we can also cancel this one. In this case, we have our formula to get the acceleration on Earth. Since it's interacting on Earth, we have the gravitational constant, the mass of Earth, and just divided by the radius of the Earth. Before I will forget, it's the radius of the Earth. So we have the values here, very necessary figures in doing this kind of problem. We have the gravitational constant, the mass of Earth, and then the radius. This value is radius based on equatorial radius, meaning the largest radius measured, because yeah, it's in equator, and Earth is, you know, not a full circle but a spheroid with a bulge structure, bulge like shape around it. So this is the radius that we are referring here with this value. All right, let's plug in all the values. For G, plug in carefully. 6.673 times 10 raised to negative 11 Newton meter squared, and kilogram squared. Then you have to multiply it by the mass of Earth, 5.97, for 2 times 10 raised to positive 24 kilogram. And we will divide it by the radius of the Earth, the equatorial radius, that's 6.3781 times 10 raised to 6 meters, and don't forget to get the square of it. Let's try to see if we have something to be cancelled, especially the unit. In this case, we can cancel, since this is in the numerator, we can cancel 1 kilogram, and we have 2 kilograms here, so just cancel this one. Let's multiply 6.673 times 10 times 10 raised to negative 11 multiplied to 5, the mass of Earth, 5.974, 2 times 10 raised to 24. And it will give us a product of 3.98658366 times 10 raised to 14. And the remaining unit in the numerator, we have Newton meter squared per kilogram. We will still be extracting the value of n, as we all know. N is kilogram meter per second squared. Okay, later. And then the squared of the squared of our Earth's equatorial radius, we will try to figure it out. 6.3781 times 10 raised to positive 6 squared. So our the squared of the radius of the Earth is 4.068015961 times 10 raised to 13, and meter times meter, meter squared. I would like to clean this unit first. We have Newton is equal to kilogram meter per second squared. I will write it again. So the Newton could be written as kilogram meter per second squared multiplied by our meter squared per kilogram. So we have Newton here, and we have this unit here. Please pay attention. So in doing so, we can cancel kilogram here, and we will multiply meter times meter squared. So that's cubic meter over s squared. So we can replace to this value. So we can write it as m cubed s squared. Now we will divide 3.98658,366 times 10 raised to positive 14 divided by 4.06, 4.068015,961 times 10 raised to positive 13. And we have our answer here. It's 9.799823,054, and the unit will be canceled. Like we have 2 meters here, cancel, and we have 3 meters here. Doing dividing of exponent m3 divided by m2, so we just have to get the difference of 3 minus 2, that's m1, right? So we can cancel this cube here since we get 2 meters from it, so it will have remaining 1 meter there. So it makes sense because the unit of our acceleration is meter per second squared. So we will put it here, meter per second squared. Or approximately, this is the 9.8 meter per second squared, the famous acceleration due to gravity on Earth. So if you like my content, yeah, don't forget to support to this channel. Your like and your comments will help this channel to be noticed. So don't forget to subscribe to this channel, and thank you, and see you for more videos like this. Bye for now.